In this lecture, we're going to cover electric force in 2 dimensions. Until now, we have only looked at the force between 2 or 3 charges on a line. But if we have 3 or more charges that do not fall on a line, we must add the forces just like we added vectors that were at angles to one another. This was done in kinematics for your projectile motion problems, dynamics, and momentum problems. We're now working in 2 dimensions. First, we establish perpendicular axes that are symmetric to the problem. For example, let's calculate the force on the charge at point C from the charges at points A and B in this diagram. The charges at each point are equal to plus Q, and since we have a triangle with 3 equal sides, what is the value of theta? So again, we need to figure out what is the angle of theta. Let's choose some axes for the problem to take advantage of the symmetry of the charges as well. In this case, the standard Cartesian coordinate system centered at point C works well. Then let's draw the forces acting on the charge at point C due to the charges at point A and point B. Again, you should have gotten a 60-degree angle for theta. Now we're ready to find the force on C by A and the force on C by B. Since the charges at point B and C are equal in magnitude, the magnitude of the force on C by A and the magnitude of the force on C by B are going to be equal in magnitude. Next, we're going to break these 2 forces into their components by using sine and cosine. We already know that the angle here of theta is the same as the angle here, which is a 60-degree angle. I'm also going to change the labeling, so it matches what you've been taught in class. Because it's the force on C by A, and it's the force on C by B. Okay, so now we can see that the x components of the force are equal in magnitude but oppositely directed. And that means that when they add up together, these 2 force components here and here are going to give us 0. Again, this is going to be force on C by B, and this is going to be force on C by A. And that's going to be in the y direction. So what happens is these 2 forces here, the x components of both the force on C by B and the force on C by A, are going to be equal in magnitude, oppositely directed, so when you add them together you get 0. That leaves us just the force on C by B in the y direction and the force on C by A in the y direction. They're in the same direction, so that means it's time for us to actually do some calculations. Okay, so remember that you need to start out with the sum of the forces in the y direction is equal to ma sub y. Okay, so we're going to go ahead and add them up. The force on C by A is equal in magnitude to the force on C by B because they're all the same charge. That means that's equal to kq squared here. kq squared over r squared. Okay? If we find the net force in the y direction, it's going to be force on C by A in the y direction and force on C by B in the y direction. If we look at the y component right here, we end up with opposite over hypotenuse. That's going to be sine theta. Okay, so in order to find the y component of the force on C by A and the force on C by B, we're going to have to multiply this force here by the sine of theta in order to get the component, the y component. That ends up giving us 2f sine theta, where this f right here is force on C by A, which is also equal to the force on C by B. Remember that they are equal because they have the same charge. So the force in the y direction is going to be 2 times this individual force. So 2kq squared over r squared times the sine of theta. In this case, theta is 60 degrees. This ends up giving us the square root of 3k times the q squared over r squared. Now, the x component is just going to be 0, which we see here, 0 newtons. So that means the total force for this problem is going to be in the y direction only, and this is going to be the magnitude, the square root of 3 times kq squared over r squared. And the direction in this case is going to be north. And the reason we get that is because we're using symmetry. Okay, so 3 positive charges with an equal charge of Q are located at the corners of an equilateral triangle of side R. What is the direction of the net force on charge A, right here, due to charges B and C? Go ahead and pause the video now. Okay, so let's see what you chose. Hopefully you chose C as your correct answer. Remember, it's not going to be straight up because we're not looking at C anymore. We're looking at A. So the net force is going to be in this direction. Actually, let's look at that again. Net force on A due to charge to B and C. Well, this is going to be directed which way? It's going to push it this way. This is going to push it this way. So the net force is going to be this way at an angle. Okay, what is the magnitude of the net force on charge A due to the 2 charges B and C? So now we're looking at for a value. So go ahead and pause the video. Okay, so let's see if you have the correct answer. The correct answer is D. You should end up with the square root of 3 times kq squared over r squared. 4 Q charges are arranged in the corner of a square as shown in this diagram. What is the direction of the net force on the test charge Q placed at the center of the square? Go ahead and pause the video now. Okay, since it's a negative charge, this Q will push it away. This one will push it away, so the net force will be to the right. These two will be pulling it this way and pulling it this way, so you'll also have a net force to the right. So the correct answer should be D. In the next video, we'll talk about electric field.